This next area of the topic has to do with game theory, which is a somewhat relatively new area of economics. It's been around for a while, but it's a somewhat newer branch that gets a bit of attention. So game theory is the study of strategic decision making, which up to the point in this class, we've been talking about decision making, about comparing benefits and costs, but now we want to introduce the concept of strategic decision making. In an economic context, what do we mean by strategic decision making? So I've got a couple of different pictures of some different situations that all involve strategic decision making. And we'll go back to my classic example of me stopping and getting a cup of coffee on my drive into work. I'm going to assert that my decision to get a cup of coffee, nothing strategic about that. But these games, they are strategic. So think for a second about what might differentiate regular old decision making from strategic decision making. The difference is me getting a cup of coffee, those benefits, those costs, pretty much I'm the only one affected by it, right? If I decide not to get my cup of coffee, is anyone else affected by that decision? No, I mean, they lose a little bit of revenue, but do they notice that revenue? Nah, not really, right? Whereas when we look at these other kinds of situations, these are situations where you've got decision makers, and whatever choice they make, it influences others' choices, right? The decisions that they could make, the outcomes from those decisions, and usually there's some interrelatedness to decision makers and the outcomes, right? That's the key part of strategic decision making. So we tell the classic motivator for game theory is to think about two different bank robbers, right? So that's the basic story that we have that gets told in many of these textbooks is you've got bank robbers, and they go and they rob a bank or commit some kind of crime, and they almost get away with it, right? So they commit the crime, they leave some evidence behind, and then at some point in the future, the cops bring them in on some unrelated charges, and they think that they've got some evidence to suggest that they did this earlier crime, but they can't quite prove it slam dunk in court. So what do? They take these two prisoners, they separate them in two separate areas, and then they try to isolate them and get one or both of them to confess to the crime, to turn evidence on the other. So that's the classic example of this first type of strategic situation that we're going to call a prisoner's dilemma. That's a pretty well-known name. We're going to focus on a single period simultaneous move game. So a game is just, in this context, is really any time that we have strategic decision making going on. And again, strategic decision making is when your decision and outcomes are influenced and influence others' decisions and outcomes. Single period, meaning we're going to look at a single time period, right? Later on, we can consider multiple time period decision making, but this first version, we're just going to look at a single period of making a decision. And we're also going to look at what we call a simultaneous move game. So a simultaneous move means that the decision makers are making their decision at the same time. Not necessarily at the exact same moment, but they're making their decisions, and those decisions are being revealed at the same time. One is not making a decision in the absence, or one is making a decision in the absence of knowing what the other player is doing, right? We can later consider some sequential move games that look a little bit different. Anytime that we have a strategic situation, we can summarize that in what we call a payoff matrix. A payoff matrix is just, like its name implies, a matrix that shows the payoff from different decisions. So I had a friend in North Carolina, and so I always use this example with him as a tribute to this guy's story, right? And so he was a bank robber, right? And he got caught, but they didn't have entirely great evidence for it. And so later they brought him in, and they did the exact whole situation that we described earlier, right? Whereas they separated him, isolated him, and they gave the options to either remain silent, and we'll get you on some kind of evidence, or confess to the crime and implicate your friend, right? And so we've got this payoff matrix has three main parts to it, right? Whenever we think about a strategic situation, we want to focus on three main parts to it. We've got the players, which are the entities who are making decisions. In this case, we have two individuals, Rick and Sean, who are making a choice, right? But the players could also be businesses, they could also be countries, they could be union and management, right? The players are just whatever the decision-making units are that are in the strategic situation. We've got players, we've got decisions, right? So in this case, these two players, these two bank robbers, face a symmetric dichotomous decision. It's symmetric in the sense that, right, Sean faces the decision confess or silent, and Rick faces the decision confess or remain silent, right? And it's the same set of decisions for both of them. It's symmetric because it's identical for both players, and it's also dichotomous, right? So we've got confess or silent, right? It's either going to be one or the other. There's no in between. We can say that it's a mutually exclusive, completely exhaustive list of their decisions. They're going to do one of these two things, and they can't do both. You could think about that classic game, what's it called? Rock, paper, scissors, right? That's not a dichotomous decision. You've got three decisions to make there, but we're just going to focus on a simple little symmetric dichotomous set of decisions for these two players. Players, decisions, and then outcomes, right? So we got to know what are the outcomes of the decision. So we've got two players with two decisions, so that produces a 2x2 matrix. Each element of this matrix represents the outcome. So the way that this is structured is the first value is the outcome for the person on the left, and the second value is the outcome for the person on the right. And we got to define what those outcomes represent. In this case, outcomes represent years in prison, and we can make a pretty non-controversial assumption that people care about minimizing their years in prison, right? So we've got, in this 2x2 matrix, make sure that you understand what each of the different pieces represent, right? So we've got silent. Silent is this bottom right. The top right is Sean confessing and Rick remaining silent. Bottom left, Sean is the one who stays silent, but Rick confesses. And then in the upper left, we've got both of them trying to confess and turn evidence on the other. For each of those elements, the first value corresponds to Sean, and the second value corresponds to Rick. Right? So again, we're trying to make a pretty strong distinction between players, decisions, and outcomes. And the next slide kind of summarizes this. Again, in blue, I've got my players. In red, I've got my decisions. And then in green, I've got the outcomes. And for those outcomes, in each element of the matrix, the first value is the outcome for the person on the left. The second value is the outcome for the person, in this case, on top, right? We can think about how someone would approach something. So we can think about two different strategies that a player may adopt when they're trying to make a decision. The dominant strategy is when a player looks for the best decision of a player regardless of the other player's decision. Let's take this one first because this is going to be our useful concept, right? A dominant strategy is a best decision for a player regardless of the other player's decision. And we've got, does Sean have a dominant strategy? So we're asking, does this decision maker Sean, does this player Sean have a dominant strategy? That is to say, right, we're defining it in terms of his decisions. Is his decision of confess or remain silent going to be his best decision regardless of what Rick decides? So regardless of whether Rick confesses or remains silent, will Sean find confessing or silent to be his best option? In order to decide what Sean's dominant strategy is, we have to first consider what Rick could do. So let's consider, what if Rick decides to go with the decision of, let's not do confess, let's do silent first, right? Let's consider both of these guys remaining silent. If Rick decides to remain silent, think about, what are we looking at here? If Rick remains silent, we are considering this second column. If Rick remains silent, Sean faces, let's have Sean in green. Sean faces the decision to either confess or remain silent, right? When Rick confesses, Sean can either remain silent and get 1 year in prison, or if Rick's going to remain silent, Sean could also choose to confess. And if Sean confesses, Sean will get 0 years in prison. So the two possible outcomes are, right, that Sean could either decide to remain silent or he could confess. If he remains silent, he gets 1 year in prison. If Sean confesses, Sean gets 0 years in prison. Between those two alternatives, which would Sean prefer? Sean is going to prefer to confess. And again, we're making an assumption that Sean wants to minimize his own years in prison. Think back a second about Adam Smith, right? Adam Smith said that individuals should pursue their own rational self-interest. Rational, look at your benefits, look at your costs. Self-interest, meaning look for yourself. What are your benefits and your costs, right? If Rick remains silent, Sean's best decision is to confess and get 0 years in prison. That makes sense? All right, so now let's consider, I forgot Rick was in blue, right? So now let's consider the other thing that Rick could do. If Rick decides, instead of silent, but instead to confess, what are we looking at? The column or the row? We're looking at the left column for Rick confessing, right? Again, if Rick confesses, Sean faces the same symmetric dichotomous decisions, right? His decisions are to either remain silent or to confess. If Sean decides to remain silent when Rick tries to turn evidence on him, my goodness, right? Sean is going to spend 20 years in prison. Whereas if Rick tries to turn evidence and Sean also tries to confess, if they both try to confess, Sean's only going to spend 7 years in prison. If, right? We've got this if-then conditional statement. If Rick confesses, what is Sean going to want to do? Sean wants to confess. Step back. Notice, what do we have for Sean? The question was, does Sean have a dominant strategy? In order to answer that question, we've got to think about what Rick might do to conclude Sean's decision, whether or not it's regardless of Rick's decision. If Rick remains silent, Sean's going to want to confess. If Rick confesses, Sean's going to want to confess. It sounds like, what is Sean's best decision? His best decision is to confess, and that does not matter. It does not depend on what Rick's decision is. Notice, Sean's outcome absolutely depends on Rick's decision, but Sean's decision doesn't depend on Rick's decision, right? The outcome of 0 or 7 totally is going to depend what Rick decides, but the decision was to confess. And that decision is the same regardless of what Rick chooses. So we'd say that that Sean has a dominant strategy. Yes, he has a dominant strategy, and yes, his dominant strategy is to confess. Real quick, can you think about, does Rick have a dominant strategy? And if so, what is it? Rick and Sean face a symmetric, dichotomous set of decisions, right? But also notice that their outcomes are also symmetric. So you probably have concluded by now that Rick does have a dominant strategy that matches Sean's dominant strategy. Make sure that you understand how you interpret each of these pieces, though. There's one other thing that I want to do real quick. As we go through and evaluate dominant strategy, and again, your book has this nice little ridiculous insert that describes how you can look at things. I want to think about another way to identify the dominant strategy. If we want to identify Sean's dominant strategy, we got to think about Rick. Rick can either remain silent or confess. What would Sean prefer to do? Sean is the first number, so between those two options, Sean would prefer to confess. So if you underline the pairwise value that's compared, right? If Rick confesses, what does Sean want to do? Sean could stay silent, or he could confess. Sean would prefer to confess. And notice that for Sean, if both of the pairwise preferred values are in the same row, then that decision is his dominant strategy. And we just went through, Sean's dominant strategy was to confess. It's symmetric, so let's go the other direction for Rick, right? So with Rick, Sean can either choose to remain silent. Rick's values are the second values, so Rick can either confess or remain silent. Which of those would Rick prefer? Rick would prefer to confess. If Sean confesses, what will Rick prefer to do? Rick could remain silent, or he could confess. Between those two options, Rick prefers to confess. So notice that when we underline the pairwise preference for Rick, those second values are in the same column. that column is the dominant strategy for Rick, right? So underlining the pairwise preference is a useful thing in a couple of minutes, but I wanted to make sure that we also thought about that's also a neat way that we can identify the dominant strategy. And again, please go and read your textbook on the little insert because I love how ridiculous the way that your author describes it. One strategy that a player could adopt in making a decision is to look for what's their best decision regardless of the other player's decision. An alternative strategy that a player could adopt is what we call a secure strategy. A secure strategy, we've got a definition, is the decision for a player that's the best of the worst case outcomes. So we could ask the question, does Sean have a secure strategy? So let's go ahead and delete all that pairwise stuff and just focus on this secure strategy. A secure strategy is the best of the worst case outcome. So let's think about Sean, right? We're asking, does Sean have a secure strategy? What is, if Sean confesses, what is the absolute worst thing that could happen to him, right? If Sean confesses, he's either going to spend 7 or 0 years in prison. What's the worst outcome for Sean confessing? I'm not going to underline it, but I'll put a little bubble around it. It's the 7 years in prison. That's the worst thing that could happen if Sean confesses. What's the worst thing that could happen to Sean if he were to remain silent? He's either going to end up with 1 year in prison or, my goodness, he could end up with 20 years in prison. Those are the two worst case scenarios. Now, the secure strategy is the best of those worst case scenarios. So look at those two worst case scenarios. Which one is the best? Which one's better? This is the better one, so whatever decision corresponds to the best of the worst case scenarios, that's also a secure strategy. Does Sean have a secure strategy? Yes, and it's to confess. And notice that in this particular case, the dominant strategy is the same as a secure strategy. That won't always be the case though, right? So you can think about a 401k. You may have heard of these before, right? It's a vehicle for retirement. And in general, we're going to do some broad strokes here. In general, a 401k, you want it to be made up of different assets that are going to generate some returns through time. But future returns also have some uncertainty. There's some risk in different kinds of assets. So oversimplification, we can think about stocks and bonds, right? Most people have a mix of stocks and bonds in their 401k. Stocks, hopefully you know this, if not, stocks tend to be higher volatility. They tend to be more risky, right? There's greater variability with stocks, but in the long run, stocks tend to have higher long-term average returns, right? Bonds have less variability to it, but their performance in the long run, on average, is less than stocks. That's true for most periods of financial history that we look at. Stocks, riskier, but higher returns. Bonds, safer bet, but smaller returns. So with stocks, you could lose a whole lot of money. With bonds, you don't have that much downside risk. So there's me and there's my dad, right? My dad is already retired. I'm not retired yet, unfortunately. I loved it if I could, but I'm not yet. Do you think that my dad and I have the same mix of stocks and bonds? No, we don't, right? What's my 401k allocation? It is way heavier on stocks. Why? Because I'm trying to do what? I'm trying to, right now at my age, maximize my returns. And you maximize your returns by choosing stocks. Whereas my dad, who's already retired, he's got a slightly different approach to the way that he thinks about his retirement portfolio, right? He's way heavier in bonds. Not heavier enough. I got a little normative there, but I think he should get more into bonds than what he is. But he's definitely more bonds than I am, right? Why? Because what's he thinking about? He's thinking about the downside risk, and he's trying to minimize his downside risk. In a sense, I'm using a dominant strategy. I'm trying to figure out what my best return is. Whereas my dad, in a sense, is using a secure strategy. He's thinking about the worst case scenario of stocks and bonds, and he's trying to minimize the worst case scenario from happening. He's looking for the best of the worst case scenario in his allocation. So again, who's right, who's wrong? These aren't different strategies that are one's right and what's wrong. Rather, it's a matter of approach that you bring to the table to decision making. But again, one last thing I want to emphasize, these are ways that we can think about how a player may approach decision making. The next thing that we're going to look at is called a Nash equilibrium. What a Nash equilibrium is, it's not about a player. but it's a set of decisions for everyone. We've got this formal definition, right? It's a set of decisions for all the players. So I got to talk about what Sean's going to do, and I got to talk about what Rick's going to do. And it's a combination of their decisions that fits this very specific criteria, right? I've got two players with two decisions, so I've got four possible combinations of their decisions. Let's have the first value be Sean values and the second value be Rick values. Four different combinations. Do any of these set of decisions fit this criteria such that no one player has an incentive for unilateral deviation? It's a lot of words. What does it mean? It means that no single player has an incentive, meaning they want to, meaning the benefits outweigh the cost, for unilaterally deviating. Deviating just means changing from their plan, but it's a special kind of deviating. It's unilaterally deviating. Unilateral deviations means that they by themselves are going to switch their decisions, right? If you do something unilaterally, you are the only one doing it. That's different from collectively making a decision, right? A collective deviation would be if everyone changed their decisions. And we want to consider a Nash equilibrium as very specifically defined, that it's looking at potential unilaterally deviations. No one could by themselves change their decision and be better off. If a set of decisions has that property, we say that it is a Nash equilibrium. So let's consider silent-silent, right? Where is silent-silent located? Silent-silent is located in the bottom right-hand corner. That first one, who does that first one correspond to? We've got that 1, 1. That first one corresponds to Sean's value if he remains silent, right? Sean remains silent. And Rick's my columns. Rick is also remaining silent. Rick's outcome from remaining silent is 1. So we can ask the question, would Sean be better off by changing his mind alone? Would Sean have an incentive for unilateral deviation? Meaning, if Rick sticks with the decision of silent, would Sean want to change his decision from silent to confess? Let's look at the numbers. If Rick sticks with the decision of silent, would Sean want to change his decision from silent to confess? Would he think it's in Sean's best interest for him to change his mind? Yeah, right? If Sean cares about, again, if we assume that Sean cares about minimizing his outcome of years in prison, which is a realistic assumption, then he would be better off by changing his strategy from silent to confess. Sean would want to change his decision. If anybody wants to change their decision, cross it off the list. It's not a Nash equilibrium. Notice that, my goodness, would Rick be happy with his outcome as well? Or would Rick also want to unilaterally deviate? If Sean was going to stay silent, would Rick also want to change his decision to confess? He would. Neither of them want to stick with this outcome, right? And so if anyone wants to change, it's not a Nash equilibrium, right? All right, so let's consider the next one. How about, again, Sean's the first, Rick's the second. Where is this combination located, right? Sean silent, Rick confess. Sean silent, Rick confess. This is the bottom left. Would anybody want to change their mind unilaterally? If Sean is doing silent, would he want to change to confess? Yeah, you would, right? If Sean stays silent, sticks with his decision to remain silent, when Rick confesses, he's going to get 20 years in prison. If Sean unilaterally changes his decision to confess, he's going to be better off. So yes, Sean wants to confess, or Sean wants to change his decision unilaterally, cross it off. It's not a Nash equilibrium. Notice, would Rick want to change his decision though? Think about this. If Sean was silent, would Rick be happy with that outcome? Sure he would, right? Rick would not want to unilaterally deviate, but we got to make sure that no one wants to unilaterally deviate. Sean wanted to unilaterally deviate, so we crossed that off the list. And by similar logic, but we can go ahead and fill it out, if we consider, again, Sean confessing, Rick remaining silent, that's my upper right. Would Sean want to change his decision? No, he wouldn't. Sean wouldn't want to unilaterally deviate from that outcome, but Rick sure would. If Rick wants to, I cross it off the list. Rick would not want to unilaterally deviate. So we've got one left, right? Maybe it's a Nash equilibrium, maybe it's not. Confess, confess. If they both confess, does anybody want to switch their decision unilaterally right? So if Rick confesses, would Sean want to switch from confess to silent? If Sean switched from confess down to silent, he'd be worse off. Sean's not going to want to do that. How about Rick, right? If Sean sticks with the decision to confess, is Rick going to want to switch his decision from confess to silent? No, right? What we found is we've got this property that none of them have an incentive for unilateral deviation. None of them wants to unilaterally deviate. None of them unilaterally wants to change their decision. So yes, confess is the Nash equilibrium. Notice I'm saying that confess is the Nash equilibrium. I'm not saying that 7-7 is the Nash equilibrium. That's not the Nash equilibrium. We define Nash equilibrium in terms of decisions, not in terms of outcomes. But it's a set of decision where no one wants to unilaterally change their decision. Here we go. I'm going to go back one quick way and identify a Nash equilibrium. One other quick little way, I went back the wrong one, where another way for us to identify the Nash equilibrium has to do with this pairwise comparison, right? So again, if you consider the dominant strategy, right? So does Rick have a dominant strategy? If Sean remains silent, Rick, confess, or silent, which will Rick prefer to do? Confess. If Sean confesses, Rick could silent or confess. He would prefer to confess. How about Sean? Does Sean have a dominant strategy? If Rick is silent, Sean can remain silent, or Sean can confess. What will Sean prefer to do? If Rick confesses, what will Sean prefer to do? He could be silent or he could confess. He's going to want to confess. Notice that when you do this pairwise comparison, if you underline both outcomes, those outcomes correspond to the decisions that are a Nash equilibrium. If you do the pairwise comparison and you've underlined both things, then that set of decisions is a Nash equilibrium. It's another way to go ahead and find it rather than having to write out all the different combinations and go through them one by one. Just do the underlining and you'll identify the Nash equilibrium. Question: if we look at these outcomes, right, they're years in prison. We've been thinking about these as individual years in prison, but what if we asked about collectively? If we looked at the total or the aggregate amount of time in prison, which of these decisions is going to produce the smallest total amount of time in prison? Right? So to identify the total amount of time in prison, you're going to be adding together the outcomes and think about which combination is going to be best for the group, that is going to minimize the group amount of time in prison. But recall, what does Adam Smith say? Does he say that people should be thinking about the group? No, he doesn't, right? He says that you should be thinking about your self-interest. He says that you should be thinking about your rational self-interest. Think about yourself. What are your benefits? What are your costs when you make a decision? Think about how much time in prison you're going to spend. If these individuals are following their rational self-interest, it's going to lead us to a Nash equilibrium. If each player is thinking about what's best for them as an individual, they'll know that the best decision for each of them as an individual is for them both to confess. But do those two things match up? No, right? Well, this is a case. This is why we look at the prisoner's dilemma, because it's a case where what is best for the group is not necessarily what is best for each of these individuals. If each of these individuals pursue their own self-interest, we will end up with confess. But is that what's best for the group? Lord, no, right? What's best for the group is for both of these guys to keep their mouths shut and remain silent. Why can't they get to this point? Remember, a Nash equilibrium is saying that they can't unilaterally change their mind. When you are doing something for yourself out of your own self-interest, you're doing something unilaterally. The only way that these guys could get to what's best for the group is if they didn't unilaterally make decisions, but rather if they collectively both chose to change their decision from silent. But as an individual, does Rick want to change from confess to silent? As an individual, if he does that he knows Sean's not going to want to go follow him, and he'll end up with more years in prison, right? There's this tension inherent in this prisoner's dilemma between what's best for an individual and what's best for the group. That's the point of studying this, right? Up to this point, we've said that Adam Smith, when he looked at markets, he said, hey, when markets are based on self-interest, right? We've got demand based on rational self-interest and supply based on rational self-interest. And our consumer surplus and our producer surplus, our total economic value that's created in the market that's based on self-interest is maximized. We find maximum value of economic value created when individuals pursue self-interest. And this prisoner's dilemma says maybe sometimes that's not right. When we're studying strategic situations, there's sometimes a tension between self-interest and the way that we maximize outcomes for the group. Another game theory, another strategic situation that we can look at is what we call a coordination game. So to give you a flavor for it, right? This isn't a business application, but it still gives you a flavor for it, right? I've got these two friends from grad school, Joanna and Nick, right? And so they were dating. This is the story that I tell. It's a little bit of a fictional story. The story that I tell is they're dating, they like each other, and they're trying to decide what to do on a Friday night. And so there's two movies that they can choose to see. Joanna can either go and see Eclipse or she can see Predator. And hopefully this isn't too old of a reference, but you're familiar with what these Eclipse movies were like. And maybe you even know what the movie Predator is like, Predators. But again, right, we've very much got the sci-fi horror slasher movie, which is very much up Nick's alley. And then you've got the vampire... I don't know how you describe those movies, but they were not up Nick's alleys. But they were, right? Joanna very much liked those kinds of movies, right? So we can think about, we've got our two players with their, again, symmetric dichotomous decisions. But now let's assume that the values inside the payoff, the outcomes, represent levels of utility. And remember, higher values represent higher levels of happiness or higher levels of satisfaction, right? So take a second and work through these numbers and make sure you understand what's going on, right? If we're in the bottom left-hand corner, what are we doing? Joanna goes and sees Predators and Nick goes and sees Predators. The 8 belongs to who? Joanna or Nick? Right? So the first value always corresponds to the person on the left, right? So if Joanna goes and sees a movie with her boyfriend Nick, she's pretty happy. And Nick, if he sees a sci-fi movie with his girlfriend, he's kind of at this top level of happiness, right? Alternatively, what if they both go and see Eclipse? So we have the Eclipse outcome. Joanna is going to be happy that she's seeing the kind of movie she wants to watch with her boyfriend. Nick's happy that he's at a movie with his girlfriend, but he's not too keen on that kind of movie. Whereas we can consider the off-diagonal combinations. What if if Joanna goes off and sees Eclipse by herself, and Nick goes ahead and sees Predators by himself? So they're both seeing the kind of movies that they're like, but they're not spending time together on a Friday night. Notice what happens, right? To Joanna's happiness and to Nick's satisfaction. Now, this is the ridiculous one, right? What if Joanna goes and sees Predators, a movie that she doesn't like that genre, by herself, and Nick goes and sees Eclipse by himself? Right, Joanna's happiness goes down. She's still seeing a pretty decent movie, so she's still happy. Nick is seeing a terrible, I got normative there, it's a terrible movie, right? And he's not spending any time with his girlfriend. There's nothing that he enjoys about this thing, right? So we can think about, for these different levels of utility, we can ask some questions. Does Nick have a dominant strategy? Does Joanna have a dominant strategy? Again, for Nick's dominant strategy, let's take all this away. For Nick's dominant strategy, we can do this pairwise underlining, right? So we can say that, all right, so if Joanna sees Predators, Nick can either see Eclipse or Predators. What will Nick prefer to do between Eclipse or Predators when Joanna sees Predators? He wants to see Predators. If she goes and sees Eclipse, what does Nick want to see? He could see Predators, or he could see Eclipse. Which does he prefer to do? He prefers to see Eclipse. Does Nick have a dominant strategy? No, right? His decision that's the best for him is going to depend on what she decides. If she sees Predators, he wants Predators. If she sees Eclipse, he wants Eclipse. His best decision depends on her decision. Therefore, he does not have a dominant strategy. Similarly, Joanna, does she have a dominant strategy? Well, if Nick goes and sees predators, she wants predators. If he sees eclipse, she wants to go to eclipse. Her best decision, I messed that up somewhere. If Nick sees predators, this is where the mistake is. If Nick sees predators, Joanna would prefer predators over eclipse. If Nick sees eclipse, Joanna wants eclipse. Again, her best decision depends on what he wants. She doesn't have a dominant strategy either, right? That's why we call this a coordination game. There's not a dominant strategy, but rather what would be best for these individuals is for them to coordinate their actions, right? So we can apply this not just to individuals seeing movies, but we can also apply this to different companies in the way that they try to coordinate their actions, right? Especially when we think about something like a multi-stage process. If you've got that broken up into a number of different steps to the supply chain, and you've got different companies that are in charge of different parts of the supply chain, it's really good if they coordinate their action, right? And so, again, rather than trying to compete against each other, trying to coordinate decisions can lead to a better, more efficient process, or in this case, a higher level of utility. While we're here, we can ask two other follow-up questions. Does Nick or does Joanna have a secure strategy? Let's take Nick's first, because Nick's a little bit easier to look at, right? So again, if we're thinking about a secure strategy, let's go ahead and do those in blue. If we do a secure strategy, it's looking at the best of the worst case scenarios. If Nick sees eclipse, what's the worst thing that could happen to him? He's either going to get a 6 or he's going to get an 18. The 18 is the worst thing that could happen to Nick. If Nick sees predator, what's the worst thing that could happen to him? Again, lower numbers are worse. The worst thing that could happen to him seeing predators is he gets a 5. His secure strategy is the best of those worst case scenarios. Predators is his secure strategy. Right? What I want to ask is, can you go through it and convince yourself whether or not Joanna has a secure strategy? But it's a little bit of a trick question. Why? Because look, what's the worst thing that could happen to Joanna if she sees predators? The worst thing is she gets a 6. If she sees eclipse, what's the worst thing that could happen to her? The worst thing that could happen to her is also a 6. So what do we say about Joanna and her secure strategy, right? You may be tempted to say that, oh, they're both equally the same, and so she doesn't have a secure strategy. Actually, you will always have a secure strategy, right? They both have a secure strategy. Joanna's secure strategy is either eclipse or predators, right? We would say that both of these are what we'd call a weak secure strategy. It's weak because they are both equally the best of the worst case scenarios, right? Whereas we would say that Nick has a strong secure strategy because his is by itself the best of the worst case scenarios. But if we have multiple optimal points, in this case optimal maximal worst case scenarios, then we would say that weakly both of those are secure strategy. Don't worry, anytime that I ask you as a follow-up for this, I'll always make sure that there's not this equality, but I wanted to make sure that I said that out loud, that there is a secure strategy. There's always a secure strategy. It's just this is a weak secure strategy. How about a Nash equilibrium? Remember, the easy way to find a Nash equilibrium is with this underlining. Do we have any outcomes that are both underlined? Yep. Actually, we've got 2. So the decisions that correspond to this and the decisions that correspond to this, both of those are considered a Nash equilibrium. So I'm going to do eclipse, eclipse, right? And so that's one Nash equilibrium, is for both of them to choose eclipse. And again, to verify that, just ask yourself, does anybody want to unilaterally change their decision, right? Would Joanna want to unilaterally change her decision? Nope, she'd be worse off. Would Nick want to unilaterally change his decision? Nope, he'd be worse off. That's a Nash equilibrium. How about the other one, right? So we've got predator. Predator is also a Nash equilibrium. It also had both of them underlined. Does anybody want to unilaterally change their decision, right? So Joanna, nope, she doesn't want to change her decision. And Nick, my goodness, certainly doesn't want to change his decision. So what we've got here with the coordination game, let's compare and contrast it to the the prisoner's dilemma that we had. In the prisoner's dilemma, we had a dominant strategy and and we had one Nash Equilibrium. In the coordination game, there's no dominant strategy, but we had multiple Nash Equilibriums, right? So it's possible that we could have this. What should they do? Again, what's the name of this game? It's a coordination game. What should they do is they would be best by coordinating their actions. Curiosity, though. This is loosely based on a real story, right? Some of the names and characters have been changed, but it's loosely based on a true story. Some of it. What do you think they actually did on that Friday night? Do you think that, so we've got two different Nash Equilibriums. It would be best for them to coordinate and both go see the same movie, but which one do you think they did? And lastly, we want to consider not a single move game, but what if we had multiple time periods, right? What if we had a decision that was made, not just once, but many, many, many times? So to motivate this, we've got, this is my brother Chris, and this is me. And when we were young growing up, right, we were from Michigan, we went down to Florida a few times, right? And unfortunately, we drove. This is a really long, awful car ride. It's about 26 hours, right, to get down to Florida. 26 hours in a car with two kids is awful. I can't even imagine it, right? One of the things that my parents did to try to entertain us, and my goodness, were we ever easily entertained, is at the start of the trip, they gave my brother 100 pennies and they gave me 100 pennies. And this was the penny matching game, right? And so what we would do is we'd sit in the back and we would both decide to put 1 penny down, either heads up or heads down, and we would cover it as we put it heads up or heads down in the middle seat. And then we go 1, 2, 3, we count, and we'd reveal the pennies. And the story went that if the pennies matched, then I got to keep them. If the pennies didn't match, my brother got to keep them, right? And so we can think about defining a payoff matrix based on that, right? So who is making the decisions? Chris and Matt, right? So we've got the two players. What are the decisions that are making? Again, symmetric dichotomous decisions of either heads or tails. And again, it was a choice. It wasn't that we were flipping coins. So my goodness, that makes it worse. I love my parents though. Let's have the outcomes in this matrix represent the change in how many pennies we were showing. So notice, the outcomes are either going to be that I gain a penny or I lose a penny, right? Those are my two possible outcomes. So think for a second, could you fill out this payoff matrix? Again, Chris heads, Matt heads, Matt wins. Matt is the second value because he's on top, so -1, and Chris, Matt wins, so Matt would gain a penny, and if they match, Chris loses. So we've got -1, right? If they both match, Chris, the first value, loses, and Matt, the second value, wins. Whereas if they don't match, Chris wins and Matt loses. Chris wins and Matt loses. So real quick, right, ask yourself, does Matt have a dominant strategy? We can go through the logic real quick by underlining these, right? So if Chris plays tails, Matt is going to want to do what? Matt's going to want to do tails. If Chris does heads, Matt's going to want to do heads. Matt's decision depends on what Chris does. Matt doesn't have a dominant strategy, right? And similarly, right, convince yourself that Chris also does not have a dominant strategy. Do Matt and Chris have dominant secure strategies? Sure they do, right? Because you always have a secure strategy. But again, this is one where the worst thing that could happen to Matt of doing tails is -1 or heads is -1. So it's a weak secure strategy of heads or tails. That's not very interesting. But I want to think about the Nash equilibrium. All right, so I underlined part of them, right? I've got Matt's pairwise preference for underlining. How about Chris's pairwise preference for underlining? If Matt does tails, Chris wants to do heads. If Matt does heads, Chris wants to do tails. Do any of these combinations have both outcomes underlined? No. So therefore, this is a situation. There's no dominant strategy. There's no Nash equilibrium, right? Think about the 3 different types of games that we looked at. The prisoner's dilemma, the coordination game, and now this penny matching game. Think about whether or not there was a dominant strategy, whether or not there was Nash equilibrium or multiple equilibria, and this one, penny matching. We don't have any Nash equilibriums, right? And again, think about this. Nash equilibrium, it's when no one wants to change their decision. Let's start out with tails, tails. Are we both happy with tails, tails? No, Chris would want to change his decision, right? If we were at heads, tails, though, are we both happy? No, Matt would want to change his decision. If we were at heads, heads, are we both going to be happy? No, Chris would want to change his decision. And if we were at tails, tails, heads, would we both be happy? No, right? Again, Matt would want to change his decision. There's no settling point. There's no Nash equilibrium. Someone is always going to want to change theirs. The other term that I want to put out here is this is called a zero-sum game. Why do we call it a zero-sum game? Because the only way that one of us can win is if the other loses, right? We've also got, when you've got elections in the U.S., this is my picture of the Congress, right? When we do elections to the U.S. House of Representatives or for the Senate, right? It's a zero-sum game between Democrats and Republicans. If Democrats are going to win seats in the last election, how did that happen? It was because Republicans lost seats, right? That's what a zero-sum game is. The only way that one side can win is if the other side loses. Why do I mention that and emphasize it so much? Because think about what David Ricardo argued in terms of trade. Do you remember what the punchline of David Ricardo's trade model was? It wasn't that one side wins and one side loses. Rather, what we had with David Ricardo's model for trade was that both sides could win. Both sides could be better off by engaging in trade and following their comparative advantage, right? Whereas zero-sum games, nope, there's one winner and one loser. The other thing that we want to point out again about this story of our penny matching game, oops, I didn't mean to take all that away, right? So we've got what we said with this penny matching game was that there was no Nash equilibrium, right? That we've got -1, 1, and we've got 1, -1. That there was no Nash equilibrium that was a so-called settling point where we're both not going to want to change our decision in terms of unilateral deviations. But this was a repeated game, right? We didn't just do this once on this trip to Florida. We did this multiple times. So step back and think about for a second. We take off in Michigan, we start doing this penny matching game. If we think about through the state of Ohio, we probably played this penny matching game a couple hundred times. So my question is, out of all those times that we played penny matching games, how often, what % of the time do you think it makes sense for Matt to play heads? And what % of the time do you think it was that Matt should play tails? Those two should add up to 100%. But what do you think the correct distribution of heads and tails should be over repeated iterations of this game? And also, it's symmetric, so whatever this allocation of heads and tails you came up with, it's got to be the same for Chris, right? Hopefully what you've figured out is that, my goodness, right, if I win and lose at the same rate, and those are my two outcomes, the best move for me is 50% of the time for me to play heads and 50% of the time me to play tails. What's my brother's best strategy? It's also for him to play heads 50% of the time and him to play tails 50% of the time. And as a thought experiment, let me think about this, right? So I highlight the state of Kentucky, right? What if in the state of Kentucky I decided to go with 60% heads and 40% tails? If I did that, do you think my brother would notice? Sure, of course Chris would notice. And if Chris noticed that I was playing heads 60% of the time, what's his best strategy? Is it to maintain 50-50? No, right? He's going to want to play tails 60% of the time. But if he plays tails 60% of the time, am I going to want to stick with my 60% of the time playing heads strategy? No, I'm going to lose too much, right? And so what am I going to want to do? I'm going to want to adjust my strategy and not play heads so much. Where am I back at an equilibrium, right? In a sense, there is a Nash equilibrium in this. There's a Nash equilibrium in what we call mixed strategies. Mixed strategies are not decisions, but the probability of playing a decision. There's a certain probability of playing heads and tails where we fit this earlier definition that no one has an incentive for unilaterally deviating. No one would want to, underlined the wrong thing. No one would want to unilaterally deviate from a 50-50 split in the percentage of the time that we play heads or tails. That's what we refer to as a Nash equilibrium in mixed strategies. Nash equilibrium, John Nash won a Nobel Prize for it. This is actually what he won for it, not what they portray in that movie they did a few years ago.